So the chapter 15 homework is due on the 12th. The chapter 19 homework, because we're starting chapter 19, will be due on the 19th. The chapter 15 quiz is up on Blackboard, and it will be there for a week until next Tuesday, the 17th. You have 40 minutes, and then it ends automatically. It's just like the chapter 23 quiz. You get one attempt, so make sure you have the time, and it's 25 questions, and the short answer questions need to be graded manually. And lastly, we have a lab today. So we are starting chapter 19 on the atmosphere. So we're going to go over the four major gaseous constituents of the atmosphere and talk about their abundances. We'll look at the divisions of the atmosphere based on temperature, the troposphere, stratosphere, mesosphere, and thermosphere name. We'll describe the processes and functions of ozone in the atmosphere and the process of ozone production and depletion in the atmosphere. We'll look at the distribution of insolation on the Earth from the sun, which is a terribly confusing term. It is not the same thing as insolation. We will describe the greenhouse effect. We'll discuss the latent heat of evaporation and condensation. We'll look at the process of heat conduction on the Earth's surface and describe how the temperature of the atmosphere and varies with altitude. We'll describe what's meant by air pressure and how it's measured with a barometer. We'll name and describe the fundamental atmospheric measurements essential to determine overall weather conditions, temperature, pressure, humidity, wind speed, direction, and precipitation. We'll discuss the difference between absolute humidity and relative humidity. We'll discuss the data that goes into the heat index. We'll describe what the dew point is and how it relates to precipitation. We'll describe how a psychrometer measures relative humidity. And we'll go over how to use psychrometer tables and be able to calculate relative humidity, maximum moisture content, actual moisture content, and dew point. We'll describe what causes wind and air currents. We'll describe isobars and the general movement of air between different isobars. We'll look at the formation of sea and land breezes. We'll describe the Coriolis force and how it affects the rotation of winds in the northern hemisphere. We'll differentiate between cyclones and anticyclones. We'll discuss jet streams, and we'll describe the differences between the four cloud types: cirrus, cumulus, stratus, and nimbus. And we'll go over how clouds form. So the atmosphere is the gaseous shell or envelope of air that surrounds the Earth. It's quite small compared to the size of the Earth. It's relatively thin. It does go up to a good height, 100 kilometers or so, more than that actually. It sort of fades out as you get to space. But 100 kilometers is the official line for space. So here's a video about sort of an introduction to the atmosphere and various phenomena in it. Most of the phenomena we see are quite low in the atmosphere. So meteorology is commonly applied to the study of the lower atmosphere. In the past, meteorology was actually the study of, well, everything above your head, basically. It was used to more generally describe the study of the entire atmosphere. Meteorology and meteor, as in, the rocks falling from space, come from the same source, etymologically. And the conditions of the lower atmosphere are what we call the weather. And in this chapter, we'll examine the atmosphere's composition, properties, and its mechanisms. So most of what we observe about the atmosphere is the lower atmosphere. We live in the lower atmosphere, and most of the atmosphere is in the lower atmosphere. So our atmosphere, the air we breathe and such, is a mixture of gases, and it holds varying amounts of suspended liquid droplets and solid particles. Two gases make up about 99% by volume of air near the Earth. These are nitrogen and oxygen. Both of these are diatomic, N2 and O2. It's about 80% nitrogen, 20% oxygen. I think it's about 68 and 21. Then next we have argon, which is about 1%, 0.9%. That's the next most common gas. And after that is carbon dioxide, which is only 0.03%. Name? Those are the other major constituents of air. And small quantities of many other gases are found in the atmosphere, and varying amounts of water vapor are found in the atmosphere, which is why water vapor isn't included in this, because the amount of water vapor could vary a lot. So dry air, so we're talking about dry air, is composed primarily of only two constituents, nitrogen and oxygen, 78% nitrogen, 21% oxygen, 0.9% argon, and 0.03% carbon dioxide. And I think that number is edging towards 0.04% at the moment. Carbon dioxide levels have been going up. The CO2 slice is shown much larger than scale, so it can be seen. It's actually quite small. It still has a relatively large effect. So nitrogen is about 78%, oxygen 21%, that's N2 and O2. Argon is 0.09%, argon. CO2, 0.03%. There are trace amounts of neon, helium, methane, nitrous oxide, and hydrogen. And then there are variable amounts of water vapor, which can vary from 0 to 4%, carbon monoxide, ammonia, and solid particles like dust or pollen, etc. You get carbon monoxide as pollution from incomplete combustion of various fuels. Your car has a catalytic converter to keep it from emitting carbon dioxide. That's what your catalytic converter does, for example. So carbon monoxide is largely the product of incomplete combustion in engines. So when you have lots of vehicles, you get more carbon monoxide. And carbon monoxide is nasty stuff. It'll kill you right quick because it's colorless, it's odorless, and it binds to the hemoglobin in your blood better than oxygen does. And so it's really dangerous because it basically suffocates you by clogging up your blood because it binds to your hemoglobin better than oxygen does. Though in general, the relative amounts of the major atmospheric constituents remain reasonably constant. Nitrogen, oxygen, and carbon dioxide are all involved in various life processes of plants and animals, and so they help even those levels out. They're constantly being extracted and replenished during various natural processes. So, for example, the carbon dioxide levels vary throughout the year The carbon dioxide levels in the northern hemisphere get higher in the winter when plants are less active, and lower in the summer when plants are more active. So in a process called photosynthesis, plants will consume carbon dioxide and produce O2 as a waste product. Animals, on the other hand, consume O2 and produce carbon dioxide as a waste gas. And then nitrogen is taken in by some plants and released back into the atmosphere during organic decay. So that process is more complicated. Which generally involves the way that nitrogen is taken in by plants generally involves like secondary bacteria that actually do the grabbing of the nitrogen. Plants have a symbiotic relationship. Now, the density of the atmosphere varies. So due to the gravitational attraction between the Earth and the atmosphere, the density of air is greatest near the Earth's surface. Basically, gravity is pulling the air down, so all the air above it squeezes it down. It's densest near the surface. And in fact, over half the atmospheric mass lies below an altitude of 11 kilometers, 7 miles, and 99% is below an altitude of 30 kilometers. So the vast majority of the atmosphere is near the bottom. Now, there's no clearly defined upper limit to the Earth's atmosphere. It just gets thinner and thinner until you're in outer space. It simply merges into outer space as the atmospheric concentrations get less and less. So just in general, the density and pressure of the atmosphere decreases as you go up because there's less atmosphere pushing down on it. Because the pressure of the atmosphere is just the weight of all the air above you. So as you go up, there's less air above you, less weight. And that pushes most of the air down towards the bottom. So it's a higher density as well. And there are several physical properties of the atmosphere that show distinct vertical divisions that vary with altitude. And these include temperature and ozone ion concentration. Those are two common ones. The most recognizable divisions within the atmosphere can be distinguished based on how temperature changes with altitude. And there are 4 temperature regions. So the bottom layer of the atmosphere, the one where all the weather is and where most of the atmosphere is, from the ground to about 16 kilometers or 10 miles up, that is the troposphere. We live in the troposphere. In the troposphere, temperature goes down as you travel up. It gets colder as you go up. Above the troposphere is the stratosphere. It's from about 16 kilometers to about 50 kilometers or about 10 to 30 miles. In the stratosphere, the temperature changes direction. So in the troposphere, as you increase in altitude, it gets colder. In the stratosphere, it starts to warm. And that's because the stratosphere is heated by the absorbing of ultraviolet radiation by the ozone layer, which is in the stratosphere. The mesosphere is above the stratosphere. It's from about 50 kilometers to about 80 kilometers or 30 to 50 miles. The mesosphere is another region where it cools as you go up. That's because it's very thin. It's primarily heated the other side. And then lastly, there is the outermost layer, the thermosphere, from about 80 kilometers to outer space, which is basically directly heated by the sun. And so that region is where it warms again. You don't need to memorize the specific thickness is. You just need to be able to tell with the variation in temperature. So the troposphere has over 80% of the atmospheric mass and virtually all of the clouds and moisture. Continual mixing and movement occurs here. And the lower troposphere is where weather happens. The troposphere is basically the only part of the atmosphere that's thick enough to have complicated things happen in it. So Weather basically only happens in the troposphere because it's the only part that's dense enough for it. And within the troposphere, the temperature of the atmosphere decreases about 6.5 degrees Celsius per kilometer with increasing altitude due to fewer air molecules capable of absorbing heat. And the troposphere is in fact primarily heated from below, from Earth. So the Earth absorbs light from the sun and radiation from the sun. That heat gets transferred up into the troposphere. So the top of the troposphere is very cold. It has temperatures of around -45 to -50 degrees Celsius. Above the troposphere is the stratosphere. The stratosphere and the troposphere together account for 99.9% of the mass of the atmosphere. In the stratosphere, the temperature increases in a non-uniform manner as you progress upward due to heating by the sun and the UV energy absorbed by ozone in this region. Name? So the ozone layer is in the stratosphere. And that absorbs a lot of ultraviolet radiation, so it heats up. And temperatures, once again, decrease with altitude within the mesosphere because there's basically nothing there due to the absence of air molecules. And above the mesosphere, the Earth's atmosphere becomes exceedingly thin. And this region above the atmosphere is called, the mesosphere is called the thermosphere. But the thermosphere is basically directly heated by light from the sun. And that results in an increase in temperature once again. And this extends to the outer reaches of Earth's atmosphere and into outer space. So the traditional line for outer space, the official line for outer space in Europe, that most people use is 100 kilometers. And that's in the thermosphere. So here are the sort of layers. So the troposphere is down here, temperature decreases. In the stratosphere, temperature increases. Then in the mesosphere, temperature decreases again. And lastly, in the thermosphere, temperature increases. This is sort of the official line for outer space at 100 kilometers. And there's sort of an exosphere beyond the thermosphere, and that's the edge of that space. The International Space Station is in the thermosphere, strictly speaking. Now, another way we can classify parts of the atmosphere is by looking at the concentration of ozone. Ozone, which is O3, is an unstable molecule. Because oxygen would much rather be 2 oxygens connected with a double bond rather than 3 oxygens each connected with a single bond with some like open 3 possible connections at the edges. And O3 forms from the dissociation and recombining of molecular oxygen, O2. So the way you get O3, you have oxygen plus energy. Your O2 could be split apart by, some energy. You can get it from ultraviolet light into 2 oxygens, and then that one of those free radicals can combine with an O2 to form an O3. And O3 forms most efficiently when there's the proper balance of UV radiation and oxygen molecules at about 30 kilometers in altitude. And the process of the forming and breaking apart of ozone molecules helps absorb UV radiation and convert it to heat. So the ozonosphere, which is a region between about 15 to 50 kilometers in altitude, which is characterized by its ozone concentration, it's located in the mostly in the stratosphere. It's in the upper troposphere and the stratosphere. And the greatest concentration of ozone is roughly equivalent to the stratosphere. And this ozone layer basically acts as a filter. It shields life on Earth from much of the harmful UV solar radiation. This is the kind of radiation that can break molecules apart, which could damage molecules in living things, gives you cancer, because it can damage your DNA. So, but it's breaking molecules apart up in the upper atmosphere and getting absorbed. So the ozone absorption of UV radiation explains the temperature increase in this region because it gets converted, that energy from ultraviolet light gets converted into heat. And near ground level, very little natural ozone is found. And in fact, ozone is pretty nasty stuff, and because it's highly reactive, and you don't want to run into it. It gets produced. It's a, it has certain types of pollution cause it, and also is a product of like electrical substations and things. And it gets used as a decontaminant. So you can artificially produce ozone and use it to kill stuff. And actually, it's what you use to get rid of the like reeking scent of smoke in like hotel rooms. Because it reacts with the things that make smoke stink and breaks it down. It's ozone. Oh no, there's like these machines that generate it electrically, and you just fill the room with ozone. It's really not good for you. It does smell funny, yes, but yeah. But yes, there are these ozone generators.
The Earth is covered with a thin layer of gas we call the atmosphere. Atmospheric pressure decreases rapidly as we move away from the surface. In the region known as the stratosphere, far above the troposphere in which all our weather occurs, the atmosphere is very thin. Here, short wavelength, high-energy radiation from the sun causes dissociation of oxygen molecules. When short wavelength ultraviolet light strikes an O2 molecule, it dissociates into oxygen atoms. When an oxygen atom collides with an oxygen molecule, an ozone molecule, O3, may be formed. The O3 molecule that is formed has excess energy, the energy released when the oxygen atom combines with the oxygen molecule. If it does not get rid of that excess energy, it rapidly dissociates back into O2 and O. However, if the O3 molecule collides with any other species present, most likely an N2 molecule, it transfers the excess energy to this molecule and becomes stabilized. When solar radiation from the ultraviolet region of the spectrum strikes an ozone molecule, it may be absorbed, and the O3 molecule dissociates. The ozone cycle in the stratosphere involves formation of oxygen atoms and reaction of these with O2 to form O3. Stabilization of the newly formed O3 by energy transfer through collision, and dissociation of O3 by solar radiation. The ozone layer that is established in the stratosphere by these equilibria shields Earth's surface from the ultraviolet radiation that is harmful to living systems.
And you may have heard of the hole in the ozone layer, which is actually getting fixed. So the ozone depletion, this is a little out of date. But this is one of these.
15 to 35 kilometers above Earth's surface, a gas called ozone surrounds the planet. The ozone layer acts as a barrier between Earth and ultraviolet radiation from the sun. However, pollution has caused the ozone layer to thin, exposing life on Earth to dangerous radiation. Earth's atmosphere is made up of 6 layers. The second layer, called the stratosphere, contains the ozone layer. The ozone layer is made up of a highly reactive molecule called ozone, which contains 3 oxygen atoms. Ozone is a trace gas in the atmosphere. There are only about 3 molecules for every 10 million molecules of air. But it does a very important job. The ozone layer acts as Earth's sunscreen, absorbing about 98% of damaging ultraviolet or UV light. But the ozone layer has gotten thinner. Chemicals called chlorofluorocarbons, or CFCs, are the primary culprits in ozone layer breakdown. A CFC is a molecule that contains the elements carbon, chlorine, and fluorine. CFCs are mostly found in refrigerants, aerosols, and plastic products. When CFCs are exposed to ultraviolet rays in the atmosphere, they break down into substances that include chlorine. The chlorine reacts with the oxygen atoms in ozone and rips apart the ozone molecule. Areas of damage in the ozone layer are often called ozone holes, but that name is misleading. Ozone layer damage is more like a thin patch, with the thinnest areas near the poles. The ozone layer above the Antarctic, in particular, has been impacted by pollution since the mid-1980s. There, the region's low temperatures speed up the conversion of CFCs to ozone-damaging chlorine. About 90% of CFCs currently in the atmosphere were emitted by industrialized countries in the Northern Hemisphere. In 1989, the Montreal Protocol banned the production of ozone-depleting substances. Since then, the amount of chlorine and other ozone-depleting elements in the atmosphere have been falling. Scientists estimate that chlorine levels will return to their natural state in about 50 years. By then, the Antarctic ozone hole will shrink to smaller than 8 million square miles.
And the Montreal Protocol has been successful. One of the things that's happened is we've actually seen not only just the depletion stop getting worse, it's actually getting better now. It's actually improving now. So that's excellent. And a good sign that other large scale problem solving could be done if, politicians would actually do things. So there's also a layer or a set of layers in the atmosphere we can call that's called the ionosphere. This is a region between about 70 and 100 kilometers in altitude, and it's characterized by a very high concentration of ions. And the subregions within this are labeled the D, E, and F layers. And the ionosphere, for a long time, played a very important role in that because it's full of ions, primarily actually ions that were emitted by the sun and trapped by the Earth's magnetic field, you can bounce radio waves off of it. So that's how long-range radio communication used to work. Where if you wanted to send a radio message to someone who was far over the horizon, you could literally bounce your message off the sky. And this has some funny things because the strength of the ionosphere varies between day and night and things like that. So it's not always consistent. But this is part of also why AM range radio waves are the ones that bounce off the ionosphere. And this is why sometimes AM radio stations will have enormous ranges, because they can basically bounce off the ionosphere, bounce off the ground, bounce. And if you've heard about using shortwave radio to listen to things from very, very far away, that's what's going on. They're bouncing off that. So before satellites were available, D, E, and F ion layers were used to provide global radio communications by reflecting specific frequencies. And shortwave radio still bounces off the So here is a video about the ionosphere.
Hey, I'm Mr. Weather. Did you know there's a non-distinct atmospheric layer? It's called the ionosphere, and it's a series of regions in parts of the mesosphere and thermosphere, where high energy radiation from the sun knocks electrons loose from their parent atoms and molecules. The electrically charged atoms that are formed are called ions. There are three main regions of the ionosphere that fall in the upper part of the mesosphere and lower parts of the thermosphere. We have used the ionosphere to boost radio communications in the past before satellites became common. Radio operators would bounce the signals off the sky to extend their range. The ionosphere changes daily and seasonally. These changes can impact radio transmissions and communications as well as GPS. Scientists monitor the ionosphere so radio operators can anticipate disruptions. Watch each week to learn more.
And the ionosphere is heavily affected by things like the solar wind and solar weather. So this is how, these days we primarily send signals either through undersea cables or by, with satellites. But it used to be that people bounced it off the ionosphere, but it's inconsistent. So it's much better to have like a satellite that just receives the signal and retransmits it, or, well, most of our data goes through undersea cables just because you can put a whole lot more data through undersea fiber optic cables than you can through atmospheric radio waves. Now, one of the effects you get from interactions between the solar wind and the atmosphere are auroras. So the northern lights are aurora borealis. There's also the southern lights, or aurora australis. These are these beautiful displays of lights that are generated in the upper atmosphere, primarily over high latitude areas, because these are the regions where the Earth's magnetic field, where the ions trapped by the Earth's magnetic field impact the atmosphere. So solar disturbances provide an abundance of incoming energetic particles that supply energy for ions and electrons to recombine. So basically, high energy particles spit out by the sun get trapped by the Earth's magnetic field, and then when they slam into the atmosphere, they ionize atmospheric material, and then those things recombine, and when they recombine, they emit light. So, they knock electrons free. When the electrons recombine, it emits light. When these electrons and ions recombine, they emit visible light and other radiation. And so the colors you're seeing are things like oxygen and nitrogen that have been ionized and are recombining. And so this is a short video explaining the aurora borealis.
On Arctic nights, the aurora often flames across the winter sky. What is it, and where does it come from? This is where the tale of the aurora starts. On the sun, a star of average size among billions of other stars in our Milky Way. The sun acts as an enormous power plant. The energy is created deep inside the core of the sun. Here the temperature is over 14 million degrees, and the pressure so enormous that hydrogen atoms are squeezed together into another element, helium. This nuclear reaction releases energy. The light radiates outward from the core of the sun. In the outer layers, the heat moves to the surface in huge eddies, called convection cells. These electrical currents of charged gas create magnetic fields inside the sun. In some places, strong magnetic fields push their way up through the surface. They slow down the eddies of hot gas. The surface cools, and darker sunspots appear. The electrically charged gas is called plasma. The plasma drags the magnetic field further outwards. The magnetic field stretches and twists like a rubber band, and then the rubber band breaks. Several billion tons of plasma is hurled out from the sun. This is called a solar storm. The solar storm can reach speeds over 8 million kilometers an hour. After 6 hours, it blows past the planet Mercury. After 12 hours, the planet Venus. And after 18 hours, the solar storm reaches Earth. When the solar storm reaches our planet, something strange happens. An invisible shield, the Earth's magnetic field, deflects the storm. The magnetic fields couple together and create a funnel where the gas streams down on the daylight side of the pole. This is the daylight aurora. The magnetic fields stretch further back and couple together. The magnetic rubber band breaks, and gas from the solar storm streams along the magnetic lines towards the poles on the night side. This is the nighttime aurora.
So primarily, if you want to see the aurora borealis, you need to go either far north or far south. You know, the aurora borealis, you need to go far north. The aurora australis, you need to go far south. But if there's a particularly strong solar storm, you can see them closer to the equator. In fact, there was one recently where there was supposed to be an aurora visible here, like the Chicago area. I didn't see it, but
Too much light for you.
actually, no, I'm just old and fell asleep. I don't know if it was actually visible, but there's a famous case where there was an incredibly intense solar storm and coronal mass ejection, and the auroras were visible as far south as Hawaii. But this was a solar event so strong that like telegraph equipment was actively sparking. This was one of the biggest, recorded.
When did this happen?
1890 something, I think. It'll show up in the slides later when we talk about solar weather, I believe. But a while ago. It would be disastrous today, actually.
Oh, really?
Because it would damage lots of electric and electronic equipment. Well, no, it causes, it's a big magnetic storm, basically. So
Oh, yeah, so
it can damage electronic equipment.
Yeah.
And like the power grid and stuff can be damaged by it. But this sort of thing is tracked. There's a solar weather, solar weather is tracked and it's tracked. So the atmospheric energy content. The primary source of energy for Earth and its atmosphere is the sun. The energy in the atmosphere comes from the sun primarily. It's about 93 million miles away from the Earth. It emits a vast amount of energy. The Earth will only intercept a very small portion of that energy because the energy from the sun, the light from the sun goes out in all directions. And at the distance of the Earth, the Earth is a tiny portion of the sphere at what astronomical unit? The distance from the Earth to the sun. So the portion of solar energy that's incident on the Earth's atmosphere is called insolation, for incoming solar radiation. I think it's a terrible name because it sounds just like insolation, but that is what it is called, insolation. Now, because of the Earth's tilt and because the Earth is a ball, the insolation is not evenly distributed over the Earth's surface. And this leads to seasons. The seasons on Earth are the result of its tilt and orbit around the sun. When your hemisphere, when the northern hemisphere is tilted towards the sun, it receives more insolation. It gets warmer, you get summer. When it's tilted away, it gets less insolation. It's colder, you get winter. So over time, the top of the Earth's atmosphere receives a relatively constant amount of solar radiation, though the sun's output may vary a bit, but the surface of the Earth only receives about half of this. And that's because the other half gets, well, it gets either absorbed directly by the atmosphere or reflected away. So if we look at the incoming solar radiation, about 7% gets scattered away to the atmosphere, about 24% gets reflected by clouds, and about 2% gets reflected by the ground. And that all bounces off back into space. The Earth has an albedo of about 33%. So about 33% of the incoming light gets reflected back. About 2% is absorbed by clouds. About 22% passes through the clouds. About 15% is just absorbed by the atmosphere. About 5% is scattered by the atmosphere to the ground. And about 23% goes directly to the ground. So insolation is affected by a number of different processes as it arrives and transects the Earth's atmosphere. And only about 50% of the total insolation actually reaches the Earth's surface. And that, of course, varies based on cloud cover and things like that. So the amount of light that a body reflects is called its albedo. Of the insolation received by Earth, about 33% is returned to space via reflection and scatter. Therefore, Earth has an albedo of about 33%. The moon only has an albedo of 7% due to its dark surface and lack of atmosphere, which is why if you observe the Earth from the moon, it is much brighter and more dramatic than the moon from the Earth is. So as viewed from space, Earth is much brighter and more impressive than the moon. And why Venus is such an impressive planet is two factors. One, it's relatively close, and its albedo is like 70% because it has solid constant cloud cover. The exact brightness of Earth at any given time and place largely depends on the amount of cloud cover and the ratio of land to water. Water absorbs more light than land, and cloud cover reflects more light. So most of the direct heating of the atmosphere actually comes from the Earth, not the sun. In particular, the troposphere primarily derives most of its energy from the Earth. And this occurs in 3 ways primarily. Name? The 3 primary ways that the energy from the Earth is absorbed by the troposphere. There's just direct absorption of the absorption of terrestrial radiation. Because solar radiation hits the Earth, warms it up, it heats up, that causes it to emit radiation itself. And that radiation is absorbed by the atmosphere. That radiation is primarily infrared light. And that's why when you have things in the atmosphere that absorb infrared light well, you get heating of the atmosphere. There's also the latent heat of condensation. When water on the Earth's surface evaporates, it takes energy to evaporate water. But when it recondenses, that energy is released into the atmosphere. So when water condenses from water vapor into liquid water to form clouds, that releases water into the atmosphere. And then the last way is just direct conduction from the Earth's surface. The Earth's surface is warm, it heats the air above it. So just like any other body, anything with a temperature emits energy. It emits radiation. You emit radiation. Anything with a temperature emits radiation. So just like any other warm body, the Earth radiates energy. The wavelength of the radiation emitted by the Earth is inversely related to its temperature. So the hotter things are, the shorter the wavelength they primarily emit, which is why, things get red hot and then white hot as you heat them up. You're shortening the wavelength. And the Earth primarily radiates energy in long wavelength infrared region. And it turns out water vapor and CO2 are both really good at absorbing long wave infrared radiation. And so they are the primary absorbers of infrared radiation in the atmosphere. And this absorbed energy heats the lower atmosphere and helps maintain the Earth's average temperature. This process, where the atmosphere absorbs re-emitted terrestrial radiation, is called the greenhouse effect. So this is the greenhouse effect. And the basic thing about the greenhouse effect, we definitely want some greenhouse effect, because without the greenhouse effect, the Earth would be significantly colder and we would all freeze to death. But we don't want too much greenhouse effect. Because if you get too much greenhouse effect, then the Earth will get way too hot. And as examples, Mars is a frozen wasteland where that does not have that has minimal greenhouse effect. And Venus is a boiling hellscape because it has excessive greenhouse effect. So, we want a nice in-between level of greenhouse effect. And the reason it's compared to a greenhouse is because the windows in a greenhouse will actually absorb infrared radiation emitted by the greenhouse. It's not actually the primary way that a greenhouse works, which is sort of a funny thing, but that is a fact. So the greenhouse effect is this process by which emitted radiation from the Earth gets reabsorbed by the atmosphere by certain gases, greenhouse gases. And we'd like to control those gases so that, the Earth remains in a comfortable state for us.
The greenhouse effect is a natural phenomenon. Sunlight falls through the atmosphere to the Earth, heating its surface. Not all of the heat remains there, however. Most of it is emitted as long-wave thermal radiation from the Earth's surface into space. In this respect, the gases in the Earth's atmosphere play an important role. For the most part, they allow the short-wave solar radiation through, But the long-wave thermal radiation which is coming from the surface is partly absorbed by these gases, which means that additional heat is stored in the atmosphere, like in a greenhouse. As a result of human activity, more and more of these greenhouse gases are finding their way into the atmosphere, strengthening the greenhouse effect. The additional heat is causing climate change, with the Earth literally heating up, and with some huge consequences for the environment and people. Carbon dioxide has by far the greatest share of anthropogenic greenhouse gas emissions, which means emissions that are caused by human activity. This mainly arises when fossil fuels such as coal, crude oil or natural gas are burned. To be able to better summarise and analyse the effects of these gases, their global warming potential can be expressed in the form of CO2 equivalents. This shows how much more an individual greenhouse gas contributes to global warming in the next 100 years, compared with the impact of CO2. Accordingly, the impact of methane is 25 times greater than CO2. Therefore, in the first 100 years of its emission, 1 kilogram of methane contributes 25 times more to the greenhouse effect than 1 kilogram of CO2. In Germany, methane largely arises through agricultural livestock farming and the waste sector. The impact of nitrous oxide is 298 times greater than CO2. This mainly arises during the production and use of fertilizers and in the chemical industry. Although fluorinated gases only account for a very small proportion of total emissions, some of them have an extremely potent greenhouse impact. The CO2 equivalent of sulfur hexafluoride, for example, is 22,800. F gases are used as coolants and extinguishing agents, as propellants and in solvents, among others. In Germany, most greenhouse gas emissions arise when fossil fuels such as oil or coal are burned to generate energy. The primary source in this area is the energy industry, for example, the generation of electrical power and heat. This is followed by transport, industrial furnaces, private households, and the commercial, retail and service sectors. Other emissions are caused by the production processes in industry, agriculture, and waste management. If emissions from energy production are broken down and the share accounted for by industrial furnaces and production processes are added together, it is clear that industry, as a whole, is the second biggest source of emissions. All of these emissions intensify the greenhouse effect. For this reason, it is necessary to reduce the emissions of greenhouse gases as far as possible, or, ideally, for them to be stopped entirely. Important political measures include a transport revolution, for example, more walking, cycling and use of public transport, a switch to electromobility and, overall, significantly fewer cars and lorries on the roads. More efficient and more economical fertilisation and lower livestock numbers in the area of agriculture. And of course the energy revolution, i.e. the complete phase-out of coal-fired power generation in favour of renewable energies and the efficient and economical use of energy. Fewer man-made gases mean less warming, and every reduction in emissions makes an important contribution to the protection of the climate.
So, a great deal of evaporation occurs globally due to the insulation that reaches the surface. It requires a lot of heat to change water into water vapor. It requires 540 kilocalories of heat is required to change 1 kilogram of water into water vapor. So, enormous quantities of latent heat get transferred into the atmosphere as this energy is released during the process of condensation of the gaseous water into clouds, fog, rain, dew, etc. So it turns out, when you go from gas to liquid or from liquid to solid, that process emits heat because it requires cooling. And that, releases heat into the atmosphere. It warms up the area around it. And so that process can release a lot of heat into the atmosphere. And a significant amount of heat from the Earth's surface is just conducted directly into the atmosphere. Air is a lousy conductor. It's not very good at actually moving heat around. So this is really only effective in the lowermost atmosphere where the air is directly contacting the earth. But a lot of local weather phenomena can be highly affected by the local heating caused by direct conduction. So the temperature of the air tends to be warmer near the surface of the earth, and it decreases systematically with altitude. In order to understand the atmosphere's property and characteristics, you need to take measurements. These include things like pressure, which is a measure of how much the air is squeezing, humidity levels, how much water is in the air, the dew point, which is tied to humidity, the wind, speed, and direction, and precipitation, how much water is falling from the sky. So pressure is a measure of the force per unit area. So pressure is force per unit area. And at the Earth's surface, or wherever we are, at the Earth's surface, you experience the weight of all the atmosphere above you. And at sea level, the average pressure is around 14.7 pounds per square inch. And this is referred to as 1 standard atmosphere of pressure. So 14.7. So every square inch of your body is experiencing a force of around 14.7 pounds. One of the unfortunate things about pressure is that there are far too many units for pressure. But that is 1 atmosphere of pressure. Standard atmosphere pressure is 14.7 pounds per square inch, or 1.013 times 10 to the 5 pascals, or 1.013 bars. I could also get into torrs and millimeters of mercury and inches of, there's far too many units for pressure. So here's a video about pressure and how much this actually works. If you've ever used a straw, you've used atmospheric pressure.
Hi, I'm Jared, and I'm back for another experiment on air pressure. Again, this is going to be with lesson number 3. Very simple materials again, very user-friendly. So we have a very simple beaker here. It has a very smooth top, easy to find anywhere, and I filled it with water and red food coloring. Red, green, yellow, you don't even really need the food coloring. In fact, I probably wouldn't put it in because it could stain if it does leak. So I filled it with the water. And what I'm going to do is I'm going to place a card. This is a very simple index card. If you wanted to run this through the laminator to have some lamination on it, that way you could use it again and again and again from year to year. This was actually off a calendar. Very simple. So I'm just going to start with an index card 3x5. And all I'm going to do is I'm going to be placing this index card on top of the beaker and then flipping it upside down. And you would expect the weight of the water to just push that card off of that beaker, spill all over the table, spill all over my lap, and I don't want to get my clothes dirty, so we're going to try this scientifically. We said air has pressure, and we want kids to see that pressure pushing, holding, all that great stuff. So here's how we're going to do this. Here's the beaker. We're going to put the card on top. I'm going to hold the card with my hand, flip it, and now hold the beaker. You can see the card stays in place. Amazing, amazing, amazing. So why? Why is that happening? Well, we have air in this room pushing that card in place. And this is actually, there's a nice tight seal formed on this index card. The water is forming a nice seal, and that seal does not allow air into that beaker. If I were to just tilt the corner and allow air into that beaker, and what will happen if I keep this here long enough, air will actually be able to get through the paper as it gets wet, and I'll lose my seal. But you can see the air pushing and holding this card in place. Why? Air has pressure. It's so easy to do.
It does work. As you can see here. Now this will fail soon as the water soaks through the index card and it loses its seal.
Yeah, it's already gone.
No, that was some stuff that leaked at the beginning. But yeah. But it does hold, I just don't have a good thing to use for the seal. So air has pressure. You are being pushed on by the air. So one of the ways we can measure this is with a barometer. And the original way we used this was with the mercury barometer. So this was invented by Torricelli after Galileo's work with a column of water. And so the way a mercury barometer works is there is a tube that you fill with mercury and invert into a pool of mercury. And at the top of the tube, you have nothing. This is a vacuum. This was full of mercury when you turn the tube upside down. But the mercury is heavy and is pulling down. And so, but it's being pushed up by the weight of the atmosphere. So the difference in height between the surface of the mercury here and the top of the mercury here lets you figure out the pressure of the atmosphere. Because how hard it's pushing on the atmosphere pushes it up or down in the tube. And so that'll be about 76 centimeters or 30 inches. That's standard atmospheric pressure. 760 millimeters of mercury is standard atmospheric pressure. 1 millimeter of mercury in pressure is also known as 1 torr, because there are far too many units for pressure. So the column of mercury is supported by the weight of the atmosphere on the surface of the reservoir of mercury. The reason we use mercury is because it's the densest conveniently available liquid. And because it's very dense, the column is only 30 inches tall. If you did it with water, for example, that would have to be over 13 feet tall. Well, a lot more than 13 feet tall. It had to be 13 and a half times larger. It's like 400 inches or something like that. So the height of the column of mercury depends on atmospheric pressure. So one standard atmosphere pressure will support 76 centimeters of mercury. So this was great for measuring this, but mercury barometers are pools of liquid mercury that have to be open to the atmosphere. So they're just, and they have to be, almost a meter long. They have to be at least 76 centimeters, like 30 inches long. Pressure has a lot of units. So the SI unit is called a Pascal. It's a Newton per square meter. So atmospheric pressure is 1.013 times 10 to the 5 newtons per square meter, or pascals. The British unit would be 14.7 pounds per square inch. But there are also units that are based off of the measurement of using mercury, for example. So 76 centimeters or 760 millimeters or 30 inches of mercury. There's also the torr. 1 torr is 1 millimeter of mercury. And lastly, there are bars. Bars are a nice convenient unit that is 1 times 10 to the 5th pascals, which is a nice round number that is very close to 1 atmosphere. I think it may actually be something out of the CGS system. I'm not sure. But atmospheric pressure is 1,013 millibars. So 1,013 thousandths of a bar. So for actual weather measurements, they're primarily measured in millibars, especially because this is very useful for weather, because pressure for weather varies from around 900 to 1,100 millibars, roughly. I rounded to the nearest hundred.
Yeah, that makes sense, but like really extreme hurricane.
Yeah, no. But in the 900s to the it's less than that usually. It varies more like from 950 to
Yeah.
1060, but I'm just rounding to the nearest hundred. Now, mercury barometers are super awkward. So the danger and awkwardness of handling a column of mercury, another type of barometer has been developed. These are called aneroid barometers. There is one of them on the wall up there. As you can see, this is not a 30-inch tall column of mercury. It is a relatively small dial. An aneroid barometer uses a sealed metal diaphragm that's sensitive to pressure. So basically, you have a partially filled little metal box that can expand and contract. And as the pressure outside changes, that metal box will expand and contract. So fair weather is generally associated with high barometric pressure. Rainy weather is generally associated with low barometric pressure. And that is where I wanted to get to for today. But yeah, an aneroid barometer, it's basically a little metal container that's partially evacuated. And when the pressure goes down, it expands a little. When the pressure goes up, it contracts a little. And that's basically how all pressure measurement systems work. But yeah, I might have a little spite about there being far too many units of pressure. That might be some leftovers from when I was doing my PhD and having various pressure meters in various different units. Our setup had at least 3 different units on this.